So let us hear Chiara Piccolo from the Met Office about next generation processing and assimilation of observations.
Good afternoon. So I'm Chiara Piccolo. Just to introduce myself, I work at the Met Office in the satellite surface assimilation section. I'm not going to show any equation either. I'm sorry. And I'm not going to show any results either. So you say, oh, why are you here? Well, basically, I've been invited, thank you very much, to join the workshop because it's very interesting. But the Met Office at the moment is in a stage of replacing their observation processing system and data assimilation system. And so we're basically not doing much research. And that's why my section now is not, I don't have many results to show, but I can show you our plans for this next generation era. So basically, the next generation era means that we are preparing for the next generation supercomputers. And so we need to refresh our capability, our software, both for the pre-processing of observation and for the data assimilation, in order that they skills that they perform in this new architecture of supercomputers. So but before going to the requirements and what we have, our plans, I think I'll go back to the basics to say what is important for us, and just because there are lots of mathematicians here that work in a continuous equation and with low dimension. Well, just pitch where we are to start with. Perhaps I'm going to say very obvious things, but because I don't know very well the audience, just go from basic. So we do cycle data assimilation, and you perfectly know what it means. Is the process to absorb and incorporate, observe information in our prognostic model. But for the NWP definition for us is trying to estimate the optimal analysis in a statistical sense, and then we call it initial condition, really, that leads to the best forecast. So we don't want the best analysis, what we want is the best forecast. So it's a bit of a different problem. And we get observation, we do our analysis and then produce the forecast. That is very important information for the follow-up analysis stage. So just to make you aware, the observation I used to correct the short-range forecast from the previous analysis. And in our case, our analysis window is 6 hours for global NWP, but for regional, for example, our limited area model is an hour window. And the resolution of the model is changing depending on the regional and the global reports. And every 6 hours, we use about 5 million observations to correct roughly 10 to the 9 variables. So our problem, and SNWF does know quite well, is very large. We use 4D VAR, that is a 4-dimensional adjustment in space and time, and I'm sure all of you know about it. And the other thing that the point I want to make is the model is an integral part of the analysis algorithm. It's a very key part of it, because it tends to carry the majority of the information of the past observation into the current analysis. So what we want is the best model. So if the better the model is and the more accurate the initial trajectory, what we call the background trajectory is. So what we expect is to have very small correction to this background trajectory. So the DA should be given really small correction to that. In my section, as I said, we also look at all the observation that goes into the data assimilation solver or algorithm. And just to give you a picture here of the huge amount of observation we need to process in the 6-hour window. So here, just to give you an idea, when we started sampling or measuring the atmosphere globally, 1979. This is the rough amount of observation that we got, and in 40 years we had a massive increase of volume of observation. So the circle are trying to give you an idea of reflecting the volume for each type. So you can see the satellite was a small dot and increased massively in 40 years, but also the conventional observation has increased in volume quite a lot. And this is particular for the satellites because there are so many things flying, so many sensor flies. This is a kind of a picture both in geostationary orbit and polar orbiting. And so we need to think about all of these observations when we trying to design a data simulation system that is efficient. This is another schematic of the number of sensors per satellite that we have been trying to assimilate in the last 40 years. So as you can see, until 2000, roughly, we had only the NOAA satellite, the US satellite. In the mid of the 2000, the European satellite started kicking in and getting more information now. And in the late 2010s and in the 2010s, the Chinese satellite starting to come in. So the information that we need to process is increasing massively. But we are not only looking at satellite information, we also, in my section, need to look after all the other observation types that also what we call surface-based observation, like aircraft or balloons or synops. So there is much more than only that. So just to give you a picture, I'm going to state very basic concept, but I'm sure everybody knows what the various component we are using and how we develop it. And here I give an idea when they went operational. So we have 4D VAR, and as you know, 4D VAR implicitly involved the initial background error covariance matrix, and what over the simulation window, what we use is this perturbed forecast model that is not exactly a tangent linear model that has been designed by Mike Cullen here. And that has been operational for a while. But as you see, the climatological covariance, this is an idea of a single observation that you put at the beginning of the window, is asymptotic homogeneous, and how the perturbation forecast change the covariance at the end of the window. It tried to follow the flow, but it's not doing a very good, well, it's not a very good job. But the other problem is that every 6 hours we start again from the climatological covariance. So we reset everything to 0. So we move into the hybrid covariances that I'm sure you've heard of, where we produce a flow-dependent covariance from an EDA, and that is added again at the beginning of the window by combining it with the climatological covariance. It's still during the window get propagated by the perturbed forecast model, but you can see a bit the different response during this at the end of the simulation window. So we use ensemble DA only to calculate it at the beginning. Again, other terminology, I'm sure that you know all about it, but in case you don't, just going really quickly through that. So, in hybrid 4D VAR, the ensemble perturbation, again, to estimate B only at the beginning. And the evolution, as I said before, is done by the perturbation forecast model. In 4D ensemble VAR, instead, B is sampled for an ensemble trajectory throughout all the simulation window. So we have this method that we are using now an hybrid 4D ensemble VAR, where the ensemble perturbation are combined with the climatological covariances throughout the simulation window and not only at the start. So we have is a mixture. So what he's propagating, so we, instead of only having an hybrid covariance at the beginning of the window, we do have it throughout the window. And this has been operational since 2019. Now, this is what we have at the moment. So what I'm really talking about here is how we prepare for the next generation supercomputer. So there is a big program inside the Met Office called Next Generation Modeling System that is the aim is to try to reformulate and redesign the complete NWP system in order to exploit better the future generation of supercomputer. And one of the projects between this big program is the next generation processing and assimilation of observation, what I call NGPOW. And basically where we want to redesign completely the data assimilation system and the observation processing system. And there are lots of people involved. As I said, basically all my section is working on that. I'm the project exec, and David Simonene is the project manager. So we decided to do it in partnership with GFDW, that is the Joint Center of Satellite Data Assimilation in Boulder, in US. Basically, because this new system, and it's called JEDI, John F. for Data Assimilation and Integration, meets the majority of our requirements and has a shared vision with us, has the same vision as us. And basically, this system will provide a very good opportunity for future supercomputer, both in terms of portability, scalability, and will ease new scientific development both in DA and observation processing, because it's very modular. So we hope that our old system that is very difficult to change at the moment if we want to do new science will be improved quite a lot with this new tool. And also it provides a good framework for both observation processing and data assimilation, and also for future coupling, because the plan is that also land surface DA, potentially ocean DA, will be moving to this framework, and so it will be easier to do couple data assimilation. So here there is a quick structure of it, where we have OOPS, that is a central part of this JEDI infrastructure. That is basically the DA solver. That is completely generic because is model agnostic. So you can see here that you have different potential models that can go in, including toy models. Should be, already. And then it goes with the other components are a unified observation operator and an independent, this is the input-output kind of structure, and then there is Saber, there is the B matrix representation. I need to go faster. So in terms of plans, so our plan is we split in two, as just we create a JOPA, that is JEDI Observation Processing Application, and the aim is to replicate the science that we have at the moment at the Met Office. And we have another component of the project is called JADA, JEDI Base Application for Data Assimilation, where actually the strategy is to put Ensemble at their heart of everything we do. So the timeline is such that the current system is called OPS, and then we will replace it with this new system next year for the global model, and the year after for the regional model. And then that will be coupled with the old DA system that we call VAR, and the old model, that is our unified model. And then in summer 2025, the ELFRIC should become operational. This is our new model. And finally, in summer 2026, we will also have an upgrade of our DA system. It's called JADA. So I'll skip into that because this is basically the timeline that I mentioned before. So we've been doing a lot of work on the observation processing. It's nearly there. We still have to finish some of the ports in the global and still have to do all the pre-processing for the limited area. But we are already testing some components within the parallel suite for the parallel suite preparation. And these some results, as I said, we don't change any science, so we need to be 100% sure that we reproduce exactly what we are doing in the old system. And this shows the difference between the old and new system for the different variable for a particular sensor that is ATMS on our satellite. This is the timeline for JADA, this is our DA system. It's much more complex, as you can see, and it's the two critical parts, as you know, as the covariances. Without the covariance, we can't even build 3D VAR. And the infrastructure that, you know, because this is model agnostic, we need an interface with the model. And the progress so far is quite good. So we have created a cube sphere representation in Atlas. We have a background error covariance model for the endgame grid, that is the grid, and we are preparing for this component for ELFRIC. And also we are going away from using a standard tangent linear approach within 4D VAR, and so we are working on an hybrid version where we will do the tangent linear of the dynamical core, but for the physics we'll be using an approximation that is called hybrid TLM, and here's the reference if you want more information.
That's the ensemble method.
Yeah. But what's the clear message that we have for the Metofis is that by 2026, when ELFRIC will be operational and when JADA, this DA new component, will be operational, the deterministic global NWP forecast won't exist anymore. And so initially the project was to replace, you know, hybrid 4D VAR, what I showed you before, the current operational system, but now the goalpost has changed, and still okay because we were building the various blocks that form the new DA system, but the original plans is not anymore to replicate the current capability for the deterministic, but to move it on an ensemble system only. And so what our aim is to start building an EDA based on JEDI that will match the current performance of our system or even exceed the performance.
Yeah, sorry, Arnie. Does this mean there will be no high resolution forecast running alongside it? This would be, we'll just have an ensemble and that's it.
I'll tell you in a minute. I'll explain more now. So this is what we are doing at the moment. So we have 10-kilometer deterministic, 20-kilometer ensemble is coupled with Orca 025. We have 80-kilometer top, and we have an ensemble that is this ensemble of 4D ensemble VAR. Sorry about, hopefully you understand what it means. There's a mouthful, I understand, and it's the forecast range. And this is what we do for the regional model. We still have an ensemble. And in the future, what we are expecting to do just to have a unique horizontal resolution for all ensemble members. We will retire the deterministic forecast, but one of them, as a transition period, one of the members will be an unperturbed member, but at the same resolution all the other members, and we call control, but it's an unperturbed member. This is the way to go through the system, because a lot of our downstream products depend on the deterministic. So we are talking now with our customers, stakeholders, and services to start changing the philosophy of going from a deterministic way of thinking about the weather to a probabilistic. But it will take time. And then the same for the regional one. And the idea is, as you said, the moment we have here a deterministic, both for the global and the limited area, and we move and we build the ensemble starting from the deterministic, then to create ensemble using our deterministic realization. But we want to go change the philosophy and then say, okay, we have an ensemble, and one of those member, if needed, can be used. It could be, could be the control, but it could even be, one extreme that represents better what the customer wants. And will we start? This is again, we'll start very simple. We have, this is our normal analysis cycle where everything is unperturbed, or what we can call the perturb, the control member, if you like. And then we have a perturb analysis that comes from perturbing all the inputs to the analysis stage, so observation, model, and constraint like the SSE. And then we can use any solver for the analysis step. So we will start very simply by having an ensemble of stochastic 3D vars, and slowly we'll add enhancements like hybrid covariances and then hybrid TLM, and then when 4D var will be available, we'll be using 4D var, and then at some point, and here is within in 2024, we'll have to take a decision on efficiency and trying to balance efficiency versus the performance, the skill performance of the ensemble. And we will decide if we will go for an ensemble of independent data simulation versus what Andrew Loren called a control perturbation method, that basically we're kind of recentering within the simulation window around the control. And then we also have opportunity to do outer loop with increasing window length by using the rapid update cycling. So there are things that will come later. I'll skip the regional because of time. This is my conclusion on the timeline. So we are working on this 2 system, and so unfortunately we don't have much space for doing science or thinking ahead about new way of doing DA. So I hope that in the audience there are people keen to collaborate and to do some blue sky development for us that we can do together. And then, while we'll building the new system, and see if we can try to find a way to incorporate this new science within the new system that should be much more flexible and with much more potential. And I'll stop here. Thank you very much.
Thank you very much. Are there any comments or questions for Kara?
Yep.
I have two questions. You talk about variables. So what is a variable? So the temperature given at a particular space. Is that a variable? And so you have cover the whole.
Yeah. So the variable
that number of variables. So
the number of variables means 1 point, so latitude, longitude, and height.
Yes.
For one for temperature or wind, or actually wind is the U and V component. Yeah, that's what it means. And then you have, depending on the resolution and depending on the levels, then it multiplies. Yeah. Well, for the observation is different because we don't have the observations. The observation are in a different space. So we measure radiances, and it's an integrated, and you can't really put them. They might fall inside one of the square.
No, I got this. But if the satellite, for example, measures some profile horizontally, then he also, let's say, produces, say, a certain number of observations of that time.
Yeah. You take into account all. If it's a profile, or isn't satellites provide integrated profile, but for example, GPS radio occultation will provide a profile that is because it's on the path, is not vertical. We need to take into account that it's moving. But
yes, you have a lot of additional structure. There's a lot of, let's say, structural
there are still
dependence information.
It's true, but there are still
so
gaps.
the is probably much lower. Right?
Yeah, but there's still, well, there are two things. One is that some satellites, because of polar orbiting, you have a snapshot, and then you have a snapshot of 24 hours later. So even though they do constrain, they don't constrain in time. And so the windows, the length of the window matters because we're trying to get at least 2 overpasses, something similar, in order to constrain it. But others are not enough temporary. This is temporary, not good temporal resolution. Geostationary, we have very good temporal resolution, but perhaps because of the nature, we don't have vertical resolution. So different observation type compromise themselves, but there are still gaps. For example, in the tropics, there's no match. So it's still under the determined problem. So under constraint, I would say.
What is the number of
Or the number
physical observables. You see what I mean? It's not variable is let's say temperature, which is measured or modeled over the surface. These actual numbers of variables.
Or you mean that physical properties, like
Yeah.
temperature or
Yes. Because this is another complexity measure for what you actually find.
So, well, what are basically the prognostic variable, is it, that we use in our models? Well, there are loads.
We just a roughness.
I don't know in terms of numbers, but it's definitely, we try in DA, we constrain them by moving to a space where the variables are independent. And we have a control variable space where we do the optimization is much smaller. So we use 4 variables that capture temperature and winds, and 1 that capture humidity.
So we are, let's say,
but then time
below 100.
But I can't say no. I don't think so, because still I'm talking about physical variable, and then you need to multiply by levels and resolution. So that's still pretty big. But I think we have 4 control variables. I don't remember. One is pressure, velocity, potential, and pressure, and some humidity. But then it's for every grid point, for every height. So, but I can't tell you if it's 70 times. I don't know. It depends on the resolution.
I had your sense that I figure you talk of the number also counting each.
Yeah, but you tend to analyze the models. I think it might be, I'm talking about is model space, but then when you go in control variable space, that's reduced. But yes, it's pretty big. I mean, it's not 10 to the 9, but it might be. I can't say. 10 to the 9 is in what we're trying to constrain in model space. So looking at the variable.
That one little detail, so you said you were going to have a control member to allow people really to downstream processing. That doesn't count as part of the ensemble for measuring reliability. Otherwise, it would catch far too much weight.
So you say that it shouldn't count as a part. If it's one realization that is indistinguishable from the other members, why can it not count as part of the
it depends how you do it. If you're running one member that has no stochastic perturbations in it, and that will inherently be closer to the truth than any of the ensemble members. But it's not the representative member of the ensemble. So when you're assessing reliability, are you needed for your customers downstream? So it
Well, because if you assume that the model is perfect, but it's not, even though if you put perturbation at 0, it's still a realization of that PDF.
It looked like, one an ensemble of equally likely members to get reliability. They will all need to be, they will all need perturbations, the observations of the model in some form to make that work. And beyond, as well as that, we're constructing some way don't show anything at all. And that is like a sort of seamless forecast in a sense. You need that for your downstream customers. That shouldn't be counted as part of your ensemble reliability. Otherwise,
it will destroy reliability.
Yeah, because you just don't count. If you counted it, then it would not be. It would typically close to the trees and any of the members. So upset reliability, you just don't count it.
Yeah, we need to use the control member as a transition.
Yeah, it needs to be there.
Yeah, and then
you shouldn't count as part of the ensemble.
Yeah, okay. Thank you.
Maybe a strange question, but nonetheless interested in your view. What is your view on how to communicate these new predictive capabilities? Given that someone who put at the heart of everything, so communication with the general public, but also subsets thereof, say the maritime sector or the agricultural sector. Given that that surprised me, given in the pandemic, the amount of uncertainty which was communicated to the general public actually surprised me. I mean, with spaghetti diagrams, ensembles, and then also on memes. And then maybe I misunderstood. There has been a trend in weather forecasts that the public or sectors of the public to give less uncertainty. But while in the pandemic it was just display uncertainty. So I'm curious whether the communication strategy will also be updated to somehow or to reflect that, right?
Well, I can't really answer that because it's not my area. But what I can tell you is that we are at the moment educating initially all the people inside the office, sharing our plans to people inside the office, including forecasters. The forecasters are not using ensemble information much, so we need to think about a way to communicate that better. And there is a project that will deliver in 2 years where I'm looking, because I haven't started, I'm looking only on this how to build the ensemble. But there is a downstream what tool we need to develop to communicate the information, and there is another big chunk of the project that looks after users, how to engage with the user, to educate the user, to start communicating that and answering what they want. So it will take a while to move in that direction, but we are starting now to even internally is saying there's no deterministic is a bit.
Really interestingly enough, the pandemic has at least educated some fraction of the public, and I was surprised about that. So I mean, pandemic bad. You get on that part, maybe you can build, right?
Well, they're trying to think about the symbols and how to change how we display the forecast on our Met Office website in order to reflect more, try to let them understand more. So the people need to talk to the user what kind of information they need and what, even including the public, what kind of information they need to convey that. It's a big thing in the office, but I'm not part of it.
No,
I can't tell you more than that.
I know that.
One question.
So I guess it's more like a remark. I mean, I think when you talk about users, you of course also mean institutional users who have like very, very large prediction systems on their own, bolted onto the ensemble forecast or the product that you provide, like electricity providers, for instance, or shipping forecasts, you name it. And if you fundamentally change the product, like the configuration of the ensemble, for instance, they would have to do a major change of their system as well, right? And I guess this is something that you were thinking about, right?
No, there is. We have a huge team that look after the various different products and different customers. And as I said, first you educate them, try to understand, and perhaps provide the same product based on the ensemble rather than based on the deterministic. So that's what different people in the office are looking at how to transform. If in 10 years time I only have ensemble information, how do I create the same product if the customer insists to have the same product, or how can I create additional information on top of the product they need and educate them. So the first step is trying to use the ensemble information to get to the same product. It's the easier one, and then evolve from there. But yes, it's a big part of the office that look after services. So.
In principle, you have more information. So there would be ways to throw that away.
Yeah, exactly. But if they insist that they want that product and that's yes or no answer, then you let them provide the money for doing this. We'll try to persuade them that there is more information that can be used. It depends on the customer and the stakeholders, depends quite a lot who you're talking about. More interested in additional information.
Yeah, maybe a more presentation-related question. You said that your limited area model was assimilated by a forgiver, only forgiver.
Yeah.
What is the difference in terms of computational cost between an hourly forgiver and a simple freediver for such a model with such initialization time?
Oh God, I don't know, but loads of magnitude of difference. 3D is very cheap compared to only 4D. The problem is that
even if the window is 1 hour.
Even the window is an hour. Yeah, it's very, very expensive. So, to give you an idea, to just do some test, basic test in only 4D VAR, it takes something like to do 3 days for a day, just in testing mode and not in operational. Well, in the global, as a researcher, you can get a day per day. So it's so expensive, and it's not good. So we are going to move from 4D VAR. We are going to be ensemble only in the limited area. We don't know the strategy yet, but the hourly 4D VAR, really high resolution, is not capturing all the requirements we have in terms of probabilistic score for precipitation. So yeah, it will be changed, but it's hugely expensive.
Okay. Thank you.